Hello everybody, 3.2, we're looking at the derivative as a function today. So this is similar to what we did in 3.1, except for in 3.1 we were only able to evaluate the derivative at a specific value, an a value. So now we're going to be able to come up with a derivative as a function, and the result will still have x's typically in the answer. So the rule here that we have to follow is just like rule number 1 that we saw in section 1. Rule number 2 will not be allowed to be used in 3.2 derivative as a function because rule number 2 required an a value in order for it to work. So since we don't have an a anymore, we have to use f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x. So first example, we're going to compute the derivative of f and find an equation of the tangent line at x equals negative 3. Okay. So the first thing that we need to do is fill in our rule here. So f prime of x is equal to the limit as h approaches 0 of f of, I'm going to skip this step, of f of x plus h minus f of x over h. So in this case, f of x plus h, we're going to do x plus h quantity cubed minus 12 times quantity x plus h, big parentheses, minus parentheses, x cubed minus 12x, all over h. Okay. Remember, we are setting up a 0 over 0. We're creating this indeterminate form. Our job is to find the h over h, the factor that's causing it to be 0 over 0. In order to do that, we have to expand everything in the numerator, combine like terms, and in this process, we should be canceling out all of the non-h terms. So to expand this, we need to FOIL that x plus h out 3 times. So I'm going to do this as side work up top here. Okay, so when you FOIL the first two, you have x squared plus 2xh's plus an h squared. And then you still have another x plus h to multiply through. So then you're going to have an x cubed plus 2x squared h's plus h squared x's plus an x squared h plus a 2xh squared plus an h cubed. So combining what we can here, x cubed plus 3x squared h's plus 3h squared x's plus h cubed. So it's a 1, 3, 3, 1 pattern if you're following that rule. So limit as h approaches 0 of x cubed plus 3x squared h plus 3xh squared plus h cubed minus 12x minus 12h minus x cubed plus 12x. Parentheses are so important because obviously the signs have to distribute throughout. Okay, so now we are looking for those terms that will cancel each other out. So remember, the non-h terms should cancel. So x cubed minus x cubed. Negative 12x, positive 12x. Now every term that is left still has an h in it. So my next job is to factor that. So 3x squared plus 3xh plus h squared minus 12. All divided by h still. Okay, so now we can cancel out the h's and evaluate the limit as h approaches 0. So we have 3x squared. The 3xh term will go to 0. The h squared term will go to 0, and the minus 12 stays. So 3x squared minus 12. Okay. So that is the derivative as a function. Now, the second part to this question is saying, what is the equation of the tangent line at x equals negative 3? So we structure our point, our slope, and our line. So we need a comma f of a, we need f prime of a, and we need y minus f of a equaling f prime of a times x minus a. Okay, so a comma f of a, the a value in this case is negative 3. So negative 3 comma negative 3 cubed minus 12x. So we're going to have negative 27 plus 36. So we get 9. F prime of a, so f prime at negative 3. Now we take negative 3 and we plug it into the derivative that we got. 3 times negative 3 squared minus 12. So 27 minus 12, and we get 15. So we take those two pieces and put it into our line. Y minus 9 equals 15 times x plus 3. So we have derivative as a function, and we have equation of the tangent line. Okay. Next example. We want to find the derivative of x to the negative second, and then we want to find the tangent line at negative 3. Okay, we're using the same limit definition here. Now, you can think of x to the negative second as 1 over x squared instead. Right, it's a rational function. So f prime of x, filling in the rule, equals limit as h approaches 0 of f of x plus h, which is 1 over quantity x plus h squared, minus f of x, 1 over x squared, all divided by h. Okay, so I'm not going to FOIL out quite yet. I'm going to focus on that numerator. I need to combine those two fractions. I need a common denominator. So our first fraction needs an x squared over an x squared. Our second fraction needs an x plus h squared over an x plus h squared. Remember, the whole time keeping in mind my end goal, I need to find the h over h to cancel. As soon as I can do that, I've gotten rid of the indeterminate form, and then I can evaluate. Okay? All right, so my numerator now becomes x squared minus quantity x plus 2, I'm sorry, not 2, x plus h squared divided by x squared times x plus h squared. That's really the numerator coming together, and the whole thing is divided by h or multiplied by 1 over h. So I'm rewriting the division of h as a multiplication as 1 over h. Okay. My next line of work, I need to FOIL out the x plus h quantity squared in the numerator only. Don't do it in the denominator. Okay. So limit as h approaches 0 of x squared minus, I'm going to keep the parentheses for another line of work. And so what I'm doing right now is x plus h times x plus h. So that's going to give me an x squared, 2xh's, and an h squared, divided by h, right? That 1 over h is now put in, x squared and x plus h squared. Okay. Now I'm going to subtract in the numerator, looking to cancel out non-h terms. So x squared minus x squared is 0. I have a minus 2xh, and I have a minus h squared left. factor the h out of the numerator. Negative 2x minus h is left. And divide that h out, or cancel it out. Now we can evaluate the limit as h approaches 0 because the indeterminate form is gone. So remaining h's are replaced with zeros. So we have negative 2x divided by x squared times x squared. Negative 2x divided by x to the fourth. Simplify, negative 2 divided by x cubed, or negative 2x to the negative third. Both of these are equivalent and acceptable. Okay, so that is our derivative as a function. Remember, the follow-up question here is what's the tangent line at x equals negative 3? So point, slope, line. Point is the original equation, x to the negative second, or 1 over x squared, with negative 3 plugged in. So it's negative 3, comma, 1 over 9. Slope is slope with the negative 3 plugged in. Which is 2 over 27. And line, pull it all together. Y minus 1/9 equals 2 over 27 times x minus, x plus 3 is what I should have written. In case I ran out of. Okay, this was just an additional page, so we were able to fit it, so ignore this. Moving on. So other ways to notate the derivative, and I think if there's one thing that gets confusing, especially early on, is the notation. If we don't pay attention and understand that all of these things are essentially saying the same thing, depending on the format that we're in, then it's going to get quite confusing. Okay, so df over dx is implying take the derivative of the function named f with respect to x. That is the same exact thing as saying f prime of x. The next one, dy over dx, is the same exact thing as y prime. Take the derivative of the equation named y with respect to x. Now, next to it is more specific. So now it's saying take the derivative of the function named f with respect to x when x equals 4. The other way that we could write this would be f prime of 4. Same idea with the last one. The derivative of the equation named y with respect to x when x equals 4. Okay. So we're going to find the derivative now of 5x cubed minus 2x plus 1. So y prime, we can use that notation, or we can use dy over dx, okay, is equal to the limit as h approaches 0 of f of x plus h, or y of x plus h. So 5 times x plus h, quantity cubed, minus 2 times quantity x plus h, plus 1. Big parentheses around that, minus the y equation, also big parentheses around that, separated with subtraction, all over h. Okay, so we've created this 0 over 0. Now we need to find that factor to cancel it. Okay. Simplifying in the numerator, combining like terms, that requires us to FOIL out that x plus h 3 times and distribute of 5. Remember that we did already do the x plus h 3 times, so I'm just going to put that in right away. You can look back in the notes a few pages. But you should get an x cubed, a 3x squared h, a 3xh squared, and an h cubed. And now we just have to distribute the 5 to it. Okay. So that will give us limit as h approaches 0 of 5x cubes plus 15x squared h's plus 15xh squareds plus 5h cubes minus 5x cubed plus 2x minus 1, all divided by h. Okay. So looking to see what's going to cancel out for us. The non-h terms, 5x cubed minus 5x cubed. Oh, I made a mistake, you guys. Let me backtrack. What I forgot to write in there, I got so busy with the 5 times x plus h cubed part, I forgot about the minus 2 quantity x plus h and the plus 1. So let me backtrack a little bit and fill that in. So minus 2x minus 2h plus 1. Then I have the minus 5x cubed plus the 2x minus the 1. Sorry about that. Okay, so back to where we were. Now we're looking to cancel things out. So the 5x cubes are gone. The negative 2x with the positive 2x. The 1 with the negative 1. Okay. Factor the h out of the remaining terms up in the numerator. So that would be an h. 15x squared plus 15xh plus 5h squared. And minus a 2. All over h. H's cancel. Evaluate at 0, so 15x squared. 15xh goes to 0. 5h squared goes to 0. Minus 2 is the derivative of of y. Okay, so important page here. Some functions will not be differentiable for all x values. The example here we're looking at is continuous, but it is not differentiable. And I'll talk about this in a few ways. First, we want to show that f of x equaling absolute value of x is continuous, but not differentiable at 0. Specifically at 0 we're looking at, everybody, nowhere else right now. Okay, so for continuity, right? Function is defined, limit exists, and the two are the same. That proves continuity. So f of 0 equals the absolute value of 0, which of course is 0. I'm going to throw a quick sketch of the graph up here. Absolute value curve, well, not curve, is a V-shaped function. And in this case, the parent function of it, the vertex is at 0, 0. Right? So we have essentially two lines coming together, and their slopes are 1 and negative 1 respectively. Okay, so we need to then do the limit as x approaches 0 on the left of absolute value of x. And we can see, graphically speaking, it approaches 0. The limit as x approaches 0 on the right of absolute value of x, graphically speaking again, is also 0. They come together at that point, at the vertex. Because all three of these are the same, we can then conclude that f of x is continuous. Okay. But if we want to look at the differentiability component, okay, so f prime of 0 equals the limit as h goes to 0 of f of a plus h, which is f of 0 plus h, minus f of a, or f of 0, all over h. So we have the limit as h goes to 0 of absolute value of h minus absolute value of 0 all over h. So we're saying the limit as h goes to 0 of absolute value of h over h. So if we break this apart and we look at the left and the right limits from here, right, because I'm not too sure. If I plug in 0, it's a 0 over 0. It's indeterminate form. I can't do that. So I have to take a look at, well, what's really happening. I have to take a look at the left and at the right. Now, if I think of a number to the left of 0, the main thing I'm thinking about is the fact that it is negative, right? So if I put in negative 1/10 into the absolute value, the numerator goes positive, but the denominator remains negative, and therefore the result is negative. If I think of a value on the right-hand side and I do the same limit, the numerator is positive. The denominator is also positive in this case, and therefore I come out as positive. Now, because I do not get the same answer here at the end, that would imply that it is not differentiable, right? The limit definition came up with two separate answers saying that we do not have something that is differentiable at this moment. Okay. The reason that I just got a -1 and a 1, or a negative and a positive, is because the idea of these two lines are coming together with slopes that are different, right? So any value, change my color, any value that I pick on the left side of this graph that I want to find the derivative at is going to come back with a -1. The slope of the tangent line is always going to be -1 over here because it's a line, right? A tangent line to a line is the same line, therefore the slope would always be the same. So you're always going to get -1 there. If I do the same thing on the right, anything to the right of 0, any tangent line will always come out as 1. But right here at the vertex, what do I get? I don't know. Am I on the left? Am I on the right? Am I right there? The answer is it is not differentiable. So another reason, not only because this limit definition failed and the left and the right are different, another reason that we look at, okay, we think about this is, can we zoom in, right? If we were to zoom in on this point, and the fact that it's a corner means that if we zoomed in, it would always be a corner. And therefore, at a corner, my tangent line and your tangent line might be entirely different, right? I could sketch a tangent line in so many different directions with so many different slopes. That is also what makes this not differentiable, okay? So an important note at the bottom of the page, differentiability implies continuity, but continuity does not imply differentiability. Okay. Oops. Okay. Knowing information about the derivative can help visualize the graph of the original function and vice versa. So graph A that is shown is the graph of the original function. Keeping in mind, ordered pairs of the original function would be x comma f of x's. Okay. We have our x's pretty well shown on the graph. We have our y values shown on the graph. We want to analyze this, and then we want to try and come up with a sketch of the derivative graph, okay, and see if it holds true. So we want to be able to analyze different components. We have on the original graph in blue, we have these pink tangent lines showing the slope. The other thing that they are showing, tangent lines showing slope, are showing the derivative, right? So we're able to make statements about increasing, decreasing, turning points, etc. So for example, the intervals from 0 to 2, along with 6 to 8, right? The function is increasing, right? That's a statement that we've said, from Algebra 2 onward, which also implies that the derivative is positive. Okay. The intervals 2, 6, singular, the interval 2 to 6, f of x is decreasing. And therefore, f prime is negative. F prime is negative. X equals 2 and 6 are both maxes or mins, turning points. There, the tangent lines are horizontal, and therefore the derivative is 0. Okay. So now when we translate this to the derivative graph, think we are plotting x comma f prime of x. Our y values are derivatives. So we've made blanket statements essentially about our derivatives. We have said that at 2 and 6, our derivative is 0. So therefore, on the derivative graph, if they are zeros, then they are x-intercepts at 2 and at 6. We have stated that from 0 until 2 and 6 until 8, that the derivatives are positive. And between 2 and 6, the derivative is negative. So I have to come back up and go from there. Okay. Perhaps other things are happening, but this is all that we know. We also can look at the original graph was an x cubed. So I'm actually going to adjust the way I kind of curved this unnecessarily. And have them kind of come up more as a parabola. So we're not quite ready to understand why I went from an x cubed to an x squared, but that's what's happening. Okay. All right, so here we're looking to match the graph of f with its derivative graph. So we look at things like, where is the graph increasing or decreasing? So we are increasing in blue between 1 and 4 and from 7 onward. We are decreasing in red, that's already shown, between 4 and 7 and 0 and 1. Okay. We have turning points in green at roughly 4, 7, and 1. So all of that should translate to the graph of the derivative. So we have, in the second graph, in B, we only have 2 zeros, roughly 1 and 7. So that can't be the graph. That's the thing that I go to first. Graph C has 3 zeros. They coincide with the turning points that we see in graph A. Graph C also is, if it were decreasing on the original, it is negative in those same intervals. And increasing implies positive on those same intervals. So again, a decreasing goes to negative derivative. Increasing, I'll put this in more formal words soon. Increasing goes to a positive derivative. Turning points or max mins goes to a 0 derivative. Okay. So this is really day 2 of 3.2. I want you to do a warm-up. I'm not going to fill this one in for you, but you're going to compute the derivative of 1 over x minus 3. Okay, so I just wanted to refresh and remind that these are the different ways to notate the derivative. They're all giving the same set of instructions in a different way of saying it. Okay. Oh, I should have deleted this slide also. We did get to cover this. Okay. And here is a little bit more on where that corner didn't work out and other examples that are very, very similar. A function is differentiable. A function is differentiable, then it is continuous. However, a function may be continuous and not differentiable. So a function will not be differentiable at corners, cusps, which are similar, vertical tangents, jump discontinuities, vertical asymptotes, etc. Okay, so kind of similar to where we didn't have some continuity with the tangents or the asymptotes, but the corner and the cusp, those are locations where you are continuous, but you are not differentiable. Okay. All right, so I'm going to quickly give you the derivative to each of these, and I want you to, obviously on your own at home, discover what you think the rule might be, the shortcut, because going through and using the limit definition every single time would take us all year to get through this chapter. Okay. So take a moment, pause the video, figure out if you can come up with a rule, and I'm about to show you what that rule is. So this rule is called the power rule. Okay. It works for all exponents of n, and if you take the derivative with respect to x of x to the n power, it will always equal to n times x to the n minus 1. So the exponent came down as the coefficient, and we took away 1 from the exponent. Okay. The sum and difference rules, they are saying that you can differentiate each individual term on its own. So f plus g prime quantity is the same as f prime plus g prime. Similarly, subtraction works the same way. The constant multiple rule. So if there's already a coefficient there, you can keep it. It's up to you how you want to think about this, but no matter what, the existing coefficient gets multiplied by the new coefficient from the power rule. Okay. All right, so you're going to love this compared to earlier in this section. So if we want the derivative of g with respect to t when t is 1, first we find the derivative as a function using power rule. So I highly recommend to take a moment and rewrite this. We want to make sure that we have all terms written with exponents and terms in the numerator. So it's okay to have negative exponents here. So now power rule, we're going to take the exponent, bring it down as the coefficient, so negative 3t, and we're going to subtract 1 from the exponent, so we get negative 4th power, plus 1/2 times 2 is 1t, take away 1 from 1/2 to the negative 1/2. third term. -1 times 4/5 would give us a positive 4/5 coefficient. T to the subtract 1 from negative 4/5, which means take away 5/5, and you get negative 9/5. So there's the derivative as a function, the derivative at 1, which can also be written as dg over dt when t equals 1. Now we replace the t's in the derivative function with 1. So -3, 1 to the -4th, plus 1 to the -1/2, plus 4/5, 1 to the -9/5. So we have -3 plus a 1 plus a 4/5. -15/5 plus 5/5 plus 4/5. -6/5. Okay. Pause this. You guys try this on your own, and then come back and check your work with mine. And your result should look like this. So in both cases, I used the power rule. Exponents came down as coefficients. Take away 1 from your exponent. In the second one, before I began, I rewrote square roots are 1/2 powers, and the square root in the denominator is a -1/2 power. Okay, find the points on the graph of t cubed, graph of f of t equals t cubed minus 12t plus 4, where the tangent line is horizontal. What are they asking? We have to interpret this question. Where is the tangent line horizontal? What is the slope of a horizontal line? 0. So they are simply saying when is f prime of t equals 0. So our first job is to find f prime of t. Power rule. 3t squared minus 12. Set the derivative equal to 0. And solve it. Divide by 3. Factor. It's a difference of squares pattern. Or you could solve with square roots. Either way, we get plus and minus 2. Okay. Those are the x values or t values. We want to find the points, not just the win, but the whole ordered pair. So we need to evaluate the original function at 2 and at -2. So we have 2, -12. And -2, 20. So if we were to plug the original function into the graphing calculator and get a picture of it, t cubed minus 12t plus 4. This is a rough sketch, but we have here is -2, 20, and here is 2, -12. The turning points, the max and the min. The tangent lines are horizontal there. Okay, one rule that we're going to learn here, it's not the power rule, It's an exponential rule. We'll learn more other exponential rules later in the chapter, but for now this one is taught. The derivative of e to the x remains e to the x. Okay. I explain this in a simple way because if you think about the power rule, an x cubed is becoming an x squared. So for example, if we start with this kind of a graph and we derive it, we find the slopes of the tangent lines. We can interpret the increasing, the decreasing, etc. Right here I just threw a quick sketch up there. But there's a drastic change from an x cubed to an x squared. If I thought about the power rule with an exponential and I just subtracted 1 from the exponent, that just becomes a horizontal shift, right? So our slope of tangent lines don't change. So that's my most basic explanation for why the e to the x remains e to the x. We're talking about the derivative is the slope of the tangent line. It's not going to change from one derivative to the next derivative, etc. Right? So when we're looking at these equations with e to the x's inside of them, those e to the x terms stay exactly the same. So 3e to the x remains 3e to the x. Minus 5x squared becomes minus 10x. And if we want the derivative at 2, we evaluate 3e squared minus 20. So this is our slope, right? The slope of the tangent line. We need our point. That would be 2 comma 2 plugged into the original function, which would be 3e squared minus 20. Okay, coincidentally, it ended up being the same as the derivative. And then our line becomes y minus quantity, 3e squared minus 20 equals slope, 3e squared minus 20 times x minus 2. So long section, you learned quite a bit here. We looked at the derivative as a function using the limit definition, and then we established the power rule as well as the exponential rule.